In this video, I'm going to focus on Newton's law of universal gravitation. First, I want to review the weight equation. It helps us convert between the variables mass and weight, and it's especially useful on or near Earth's surface because we already know the value of Earth's gravitational field strength, 9.8 newtons per kilogram. When we are far away from Earth's surface, though, g is unknown, and we'll need a new method to solve for weight. Let's look at Newton's law of universal gravitation. The exact law is on your screen if you care to read through it. In simple terms, the concept is that every object attracts every other object, and how much they attract is mixed into the second half of the law, talking about it in equation form. Here is the equation. Fg is the force of gravity, or weight, measured in newtons. Capital G is a gravitational constant. The number is over here, and you will plug in this number every time you use this equation. M1 and M2 are the attracting masses, measured in kilograms, and r is a distance, measured in meters. We measure it from M1 to M2, and I'll be devoting a few slides later in this video to the r variable specifically. Often, when considering this law, students wonder about common household objects, like this lamp and coffee mug placed on this horizontal table. If every object attracts every other object, then why wouldn't these two objects start moving closer together when they are placed on the table? In reality, they are attracting each other, but I can think of two reasons as to why they don't start moving closer together. The first reason is with the size of these gravitational attracting forces. Because these objects are on a horizontal surface, there is a minimum amount of force necessary to overcome static friction and set these objects into motion. Well, these masses are pretty small, and when we multiply them by our gravitational constant to the negative 11th power, the force of gravity then will be too small to overcome static friction. So typically, we want to use this law only for large objects. The second reason is that these are not the only two objects in the world of this situation. The table is present, the walls of the room would be present, and maybe things like a couch or a TV would be present as well. Everything attracts everything, so there ends up being a net cancellation of these gravitational attracting forces. So typically we only want to use this law in situations where we can isolate two objects and only those two objects. So where can we use this law? We're looking for a place that only has large masses, and we want these masses to be spread out enough where we can isolate two of them. Outer space ends up being a good connection, as we are dealing only with large objects like planets, stars, and moons, and these objects are spread out enough where we can isolate two of them. Two constants you may want to add to your notes are the known values for Earth's radius and Earth's mass, as the Earth ends up being a common object included in problems with this law. Let's talk about the r variable in the equation. We mention this as a distance, but it is a specific distance. We measure it from the center of mass of object 1 to the center of mass of object 2. If we have an Earth-Moon system, we will need to add together three things to get our r variable. The radius of Earth takes us from Earth's center to edge. The distance between the objects, variable d, will take us to the edge of the moon, and the moon's radius will take us from the moon's edge to center. So by adding these three together, we go from center to center. If instead we have an Earth satellite system, now we only need to add together two things to get our r variable. Again, the Earth's radius and distance are important, but now compared to Earth, the satellite is very small. We'll consider it as a point mass in which its thickness or radius is negligible. So no matter the scenario, always measure from the center of object 1 to the center of object 2. Let's look at an example problem, one for you to try. We already know the value of Earth's gravitational field strength at its surface is a value of 9.8 newtons per kilogram. For the sake of this problem, we're going to pretend as if we don't know that, and we're going to try to prove it. If you want to pause the video and try this yourself, I'll talk you through all the steps here shortly. First step is to understand what we're solving for, which is the gravitational field strength. That's the variable lowercase g. So we need an equation that has lowercase g in it. I'm going to choose the weight equation, but the problem with it is we don't know the force of gravity, and we don't know the mass, specifically of the person that was standing on the Earth. So I'm going to put universal gravitation on the screen as well, because it's also written as being equal to the force of gravity. And since each of these equations are equal to the same variable, Fg, I can set them equal to each other, and that eliminates Fg as a variable I need to know the value of. Next, let's apply some labels to our masses. It is the person that is in the Earth's gravitational field, so we'll put MP on the left for person. On the right side of the equation, I need both masses, person and Earth. Notice that the mass of the person divides out. That's why it is not provided in this question, and also that should make sense, because no matter what mass is placed on the Earth, it will feel the same gravitational field strength. From there, I apply three numbers that I know, the gravitational constant, and the known values for Earth's mass and radius, and it will prove for us the Earth's gravitational field strength, G, as 9.8 newtons per kilogram. Finally, I want to talk about two different ways that you may be asked to solve for mass. If you are using one of your gravitational force equations, that would be a gravitational mass, and if you use Newton's second law of motion, that would be an inertial mass.